Hi, and welcome to our presentation, Which Road to Zero? Mature Storage Technologies. We're Group 2 and consist of the members Aranan, Callum, Pavan, Ryan, Yusuf and myself, Bradley.
We'll begin the presentation by introducing you to the background of the project and how we as a team tackled the problem. We'll present the different energy storage technologies that we considered and the categorization we used to define them. Following on from this, we'll present our team's proposed solution for each of these categories, explaining how we came to these decisions. Finally, we'll present how each of these categories interlink with each other in a final overview of the project. I'll now pass on to Bradley to take you through the project background.
Our project is targeted at providing a viable long-term solution providing carbon zero energy storage in order to meet the future power demands of the UK's grid and electrical infrastructure. This is required due to the movement towards carbon zero energy production, which can be sporadic in its output, and thus will need to be supplemented by storage mediums in order to guarantee reliable output in the events of low solar, wind or other power outputs used. In order to break the problem down, we identified key areas where storage can be applied and integrated to meet with the current and future demands of the grid. These areas are the following: short-term for power supplies of typically less than a day, and long-term storage that is storage that can supply a lower output over multiple days. These can be implemented at either the grid level or on a more local distributed level, such as a scale as small as per household or up to town and city scale. Heating is also another area that needs to be looked at due to its potentially high power demands as further electrification is implemented. And finally, for the transport sector, where both commercial and personal use vehicles will need to be considered. Each of these areas could have a single technology that provides the best solution, whereas others could have multiple that are applicable. Mature and novel technologies were identified, and then research was started, with a focus on mature solutions that could be commercially viable within the next 5 to 10 year period. Our storage solution is required to work with a potential of 60 gigawatts of demand based on future estimates. The technologies looked at can be split into two categories. The first, utility, covers the background areas that would dictate our specifications. This includes the things such as logistics and sources for both the electrical grid and pipelines for gas distribution. The second, storage, was our main focus, and covers the four main methods of storage available to us: that of electrochemical, for example lithium-ion batteries, nickel-cadmium, and more discussed both later and in our report; chemical, such as hydrogen and ammonia; mechanical methods, such as flywheels to store energy with momentum; and finally, thermal solutions, which store energy as heat to be extracted later such as molten salt storage. I will now pass over to Aranan for his slides.
In order to reach net zero, energy storage systems are key because they not only store the electricity generated from renewables, but also help integrate the generation into our current national grid. When exploring a solution for the utility scale application, it was important to distinguish the technologies into two different categories that had different requirements. Firstly, the short-term solution looked at technologies that offered a quick response time and a high power output up to a few hours. This was to provide reserve and response services such as frequency regulation, load leveling, and black start services, as well as transmission and distribution support for the grid. On the other hand, the long-term solution looked at bulk power management and storing a large capacity of energy up to a few days, and so focused on scalability and lifespan. For our short-term solution, we realized there's a range of technologies that are suitable to be implemented in the utility scale application, with each of them having their own advantages. There's no single right choice when choosing a technology, but rather it will depend on the factors you prioritize at the time, such as cost, sustainability, and reliability. At this point in time, lithium-ion batteries pose to be a good solution because they are well established, with over 90% of battery storage systems utilizing the technology already. They offer the fast response and high power output required, as well as having a very high efficiency and a relatively low levelized cost of storage. And so it comes as no surprise there's already 16 gigawatts worth of battery storage projects in the pipeline to be installed in the UK, with most of them using lithium-ion technology. However, there are sustainability issues. Less than 5% of lithium-ion batteries are recycled, and there are ethical issues regarding the mining of lithium and other rare earth metals. Sodium-sulfur batteries are a good alternative, at a slightly higher cost and a lower efficiency, but have the added benefit of no self-discharge. Along with this, they use a battery chemistry that uses abundant materials. There's also research that shows these batteries can be recycled to form the same battery with no loss in performance, but currently there are no recycling centres dedicated to sodium sulfur batteries. Redox flow batteries show the greatest potential in the near future, with the lowest levelized cost of storage, and are predicted to have the biggest reduction in total install costs, which are expected to come down to a third of the cost. Secondly, they have the longest lifespan and offer the most sustainable solution, but have the drawbacks of a low efficiency and a low discharge rate, which hinder it being a clear winner. However, developments in this technology to have a fast discharge will make this technology a game changer. Now I'll pass over to Pav, who will discuss the long-term solution.
Thanks, Aranan. The long-term solution targets a storage length of up to a few days. Various technologies were considered for our final proposal, with some technologies being rejected earlier than others. Molten salt storage was first to be rejected. Despite its low costs and high efficiency proving attractive, the requirement of plentiful sunlight and warm temperatures make it unsuitable for the UK. Compressed air energy storage was also rejected due to the requirement of specific rock formations required to construct caverns, as well as its very poor efficiency. The final two options were liquid air energy storage, LAES, and iron air batteries. LAES works using thermodynamic processes to store energy as liquid air before releasing the energy by expanding the liquefied air which drives a turbine. Iron air batteries operate using reversible rusting, where oxygen reacts with iron via a liquid electrolyte. In our final solution, LAES was selected as the desired technology. Although both of these technologies have low standalone efficiencies, LAES systems can boost their efficiencies greatly using co-located factories providing waste heat and/or cold, whereas an iron air battery's efficiency is fixed. LAES is also more flexible with storage length, more space efficient, and has a lower levelized cost of storage. The initial outlay is high, although this is the case for many grid-scale solutions, as the energy storage capacity required is also very high. I will now pass on to Callum, who will present energy for heating and how this impacts our seasonal storage solution.
We also had to include heating in our considerations. This is because to implement a full road to zero, heating must be electrified, as it generates 37% of the CO2 emissions within the UK. Currently, this is because it uses methane boilers. To electrify this, there are two main options that are considered: heat pumps and hydrogen boilers. Heat pumps are more expensive, however, have a much higher efficiency compared to hydrogen boilers. Hydrogen boilers, on the other, can be installed in the same principle as methane boilers, but for efficiencies of 3 to 5 times as much energy. By electrifying heating, however, this will increase the peak demand to 300 gigawatts, 5 times greater than what it would be if it was just electricity. It also introduces significant seasonal variation. As mentioned previously, introducing electrified heating will increase seasonal variation. This means that seasonal storage is necessary. There are only two options, which is pumped hydropower or storing chemically such as hydrogen. Pumped hydropower is not viable for geographical reasons. Therefore, hydrogen storage is needed. There are 5 main types of hydrogen storage: adsorption, storing it onto an element; cryogenic hydrogen, cooling it down to negative 260 degrees Celsius; metal hydrides, reacting it with a metal to form a metal hydride; chemical hydrides, converting it to another form that contains hydrogen such as ammonia or methanol; or pressurized, which is stored in large salt caverns. The only viable option of these is storing it into caverns currently, as the others are either too infant or possess significant disadvantages, such as the poor efficiencies of cryogenic hydrogen. Of these options, the most optimal one is chemical hydrides. However, owing to their toxicity and infancy, they cannot be considered. Pressurized hydrogen means that the possible better solution for heating would be to implement hydrogen boilers. However, this is strongly dependent on how technology varies. Given that it wasn't the focus of this research, it hasn't been fully looked at.
In the UK, fossil fuel vehicles currently make up 90% of road traffic and contribute to 25% of the UK's carbon emissions. On the road to net zero, the UK is aiming to make the change to zero-emission vehicles. Using renewable green energy sources, new storage technologies in recent years allow for new electric and hydrogen vehicles to replace the existing internal combustion engine vehicles. Battery electric vehicles, BEVs, use batteries to store chemical energy. These are a well-established technology that have a high energy efficiency. A range of battery chemistries exist, but lithium-ion stands out, with numerous manufacturers using this battery chemistry in their BEVs. There is lots of supporting infrastructure in the form of BEV recharge stations on main roads and in towns in the UK. The main concern that the UK may face in the future when we all use electric cars is the strain that it may cause on the grid, particularly at peak energy demand times. Large trickle-charged batteries can be implemented at recharge stations to reduce this strain on the grid, which can charge multiple electric vehicles with high-powered chargers and then recharge from the grid during low energy demand times. The lack of restrictions of both space and temperature allows for battery technologies such as liquid metal to be utilised for this application. Another supporting technology for zero-emission vehicles are hydrogen fuel cell electric vehicles. Hydrogen reacts with the atmosphere's oxygen in a reverse electrolysis process, producing only water as a byproduct. This technology is known for vehicles that have a much larger range of travel and are just as quick to refill as fossil fuel vehicles. However, the UK currently lacks much of the required infrastructure to mass supply commercial hydrogen vehicles. This technology is much more suited for long-haulage heavy goods vehicles, particularly for businesses and companies where time is a valuable resource. I will now pass on to Youssef, who will discuss an overview of our solution.
The way that all the systems mentioned previously link together is as follows. It starts from the vehicle level. Electric vehicles will charge from local storage and generation. If they are depleted or do not meet demand, they will switch to the grid and utility scale storage. The first source of electricity will be local storage to reduce the strain on the grid and utility scale storage. If local storage is insufficient to meet demand, the system managing the flow of electricity will switch to utility storage and generation to meet demand. The prioritization of local storage with the ability to switch to grid storage and generation if local supply is insufficient aids with peak shaving, reducing the number of peaks created in a day cycle. The postponement of non-essential tasks, such as charging electric vehicles to a time of low energy demand, aids the consumer by reducing the price paid for the electricity used to charge their vehicle. The postponing of non-essential tasks also helps decrease the demand on the grid by shifting non-essential draw on the grid to off-peak hours, decreasing the load on the grid during peak hours, helping make demand on the grid more uniform throughout the day. The short-term storage solutions will be drawing from the long-term storage applications to remain topped up at all times. This ensures that frequency regulation and load leveling are possible at any time, while the longer-term applications will focus on bulk power management and blackout emergency reserve power.
Thank you all for listening. Any questions will be welcomed in our breakout room.